Sir, I am Saitya from third year Triple department. My roll number is 23951 A0221. Subject HVDC transmissions. Subject code AEED28. Topic DC voltage drop control. Self self-regulating multi-terminal networks. DC voltage drop control. Self-regulating multi-terminal networks. A comprehensive exploration of decentralized voltage control strategies for resilient multi-terminal HVDC grids. The challenges: unstable DC voltage in MTDC grid, renewable integration. Multi-terminal HVDC MTDC grids serves as backbone for integrating renewable energy sources like wind and solar farms into power grid. System interconnection. These grids enable seamless power transfer between different regional power systems, creating a unified and efficient electrical networks. Control complexity. Maintaining stable DC voltage across multiple interconnector converters presents significant control challenges due to dynamic power demands. Traditional master slaves control methods relies heavily on complex communication infrastructure, making them vulnerable to communications delays, failures, and instability during disturbances. The need for a more robust and decentralized approach become evidences and incorporative more variable renewable resources. These are the challenges: unstable DC voltages in MTDC grids, renewable integration. Multi-terminal HVDC MTDC grid serves as the backbone for integrating renewable energy sources like wind and solar farms into power grid. System interconnection. These grids enable seamless power transfer between different regional power systems, creating a unified and efficient electrical networks. Complex control complexity. Maintaining stable DC voltage across multiple interconnected converters presents significant control challenges due to dynamic power demands. Traditional master slaves control methods rely heavily on complex communication infrastructure, making them vulnerable to communication delays, failures, and sustainability during disturbances. The need for a more robust and decentralized approach become evident and incorporate more variable renewable resources. Introducing drop control, a decentralized solution. Drop control represents a paradigm shift in DC voltage regulation, inspired by establishing AC frequency regulation principle. This involves approach allows each voltage source converter (VSC) to self-regulate DC voltage output based on local measurement, eliminating the need for centralized coordination. The core concept establishes a deliberate relation between active power output and DC voltage levels. When power demand increases at a converter, the voltage naturally decreases according to a predefined drop characteristics. This automatic response enables seamless power sharing among all connected converters without requiring real-time communication between them. By disturbing control intelligence across all terminals, drop control create a resilient system that maintains stability even when individual components experience distributions or communications failures. Visualizing drops. The power voltage relationship. The drop characteristic. A downward sloping line represent the relationship between DC voltage y-axis and the active power x-axis, showing how voltage decreases as power demand increases. Automatic regulation. Each converter operates along its drop curve, automatically adjusting power output in response to voltage changes without external commands. Power sharing. Converters with stepper drop characteristic contributes, leading those with shallower slopes shape more of the load, enabling the balancing. This is the visualizing drops, the power voltage relationship. The drop characteristic, a downward sloping line, represents the relation between DC voltage y-axis and the active power x-axis, showing how voltage decreases as power demand increases. Automatic regulation. Each converter operates along its drop curve, automatically adjusting power output in response to voltage changes without external commands. Limitations of classic drop control. While classic drop control provides a solid foundation, it faces several practical challenges that can compromising grid reliability and converter safely, particularly in modern grids with high renewable energy penetration. Converter overloading. Fixed drop coefficient can cause individual VSCs to exceed their rated capacity during high power demand or fault condition, potentially damaging equipment. Unequal power distribution. Static drop setting may result in imbalanced power sharing, with some converters operating far from their optimal points while other becomes overloaded. Voltage instability. Large power fluctuations can cause excessive DC voltage deviation from nominal values, affecting grid stability and power quality for connected loads. Research insight. Studies by Econ demonstrate the classic drops control struggles with converters on voltage instability, especially during disturbances grid with integrated renewable energy resources. Advanced solution, adaptive and generalized drop control. Modern research have developed sophisticated drops control variant that addresses the limitations of classic approach through dynamic parameter adjustment and enhanced fault tolerance. Adaptive drop control (ADC) adjust drop coefficients in real time based on operating condition, preventing overloading while maintaining stable voltage regulation. Research by Zihong Zinga. Headroom-based adaptive drop control (HRADC) utilizes available converter headroom to dynamically adapt drop coefficients, ensuring converters never exceed safe operating limits. This approach, validated by Xinhong Zilanga, enhances system reliances during extreme conditions. Generalized drop design focuses on creating constancy versatile drop control that maintain robust performance across various fault scenarios and operating conditions. Present comprehensive framework for generating parameters and design. Key innovatives in drop control. Recent researchers has introduced several groundbreaking improvements that enhance drop control performance, reliability, and adaptability in complex MDT-DC grid. Unified voltage drop control. Shahid Hazi Khan propose a unified approach that balances instantaneous power among all converters, minimizing voltage overshooting during transient and improving fault clearance time. The method coordinates multiple controllers' objectives simultaneously. Optimized parameter selection. Fazil focus on optimal selection of drop parameters, including AC voltage, DC voltage, and frequency drops coefficient. These strategies achieve power sharing and minimal deviation without requiring interconverter communication. DC voltage margin control integrates a voltage margin concept with traditional drop control, creating a hybrid approach that provides enhanced stability during large power fluctuation. This method maintains voltage within acceptable boundaries while distributing. Modern MTDC grids leverage adaptive drops control to create self-regulating networks where each converter independently responds to system condition while maintaining overall grid stability. This decentralized intelligence transforms how power system handle distributions and charging load demands. The future robots and self-regulation MT grids, renewable integration, enhanced stability, ongoing research. Renewable integration, advanced drop control strategies enables reliable operations of future smart grid with higher renewable energy penetration accommodating variable generations from wind and solar resources. This method ensures grid stability through efficient power sharing and reliance against distributions, maintaining voltage within acceptable limits during extreme conditions. Ongoing research continues refinement of drop control techniques, greater performance and adaptive, including based approach and real-time optimization. Conclusion: powering the future with smarter grid. Foundation of modern MTDC system. DC voltage drops control, particularly with adaptive and generalized form, serves as a cornerstone of modern multi-terminal HVDC system, enabling reliable power transmission across vast distance, self-regulations and booster. Thank you, sir.